manage questions. He knows that that's Thank you very much.
You will talk about software and asymptotic symmetries.
Thanks very much. Yeah, I'd like to thank the advisors for this great opportunity to come to Taiwan and to this conference. It's been very, very enjoyable. And so, yeah, I want to talk about some work that was done. It was working earlier. Here we go. Yeah, that's done with some students at Trinity College Dublin, Ricardo Gonzo and Spearing, and a visitor to Dublin, Diego Medrano, Sao Paulo. And then also at the beginning of the talk, I'll talk about some earlier work. And the talk sort of has, it's all, of course, on this general topic of soft limits in scattering amplitudes. It sort of has two parts, and I hope to try and make it clear about what those two different parts are as I go on. So, but the key idea is I want to talk about gauge theory of scattering amplitudes, so basically Yang-Mills theory. And these are, of course, of great phenomenological interest. Work on collider physics and so on, being able to understand and calculate scattering amplitudes in Yang-Mills is very important. And then, of course, they also have sort of a useful conceptual tool for sort of understanding the structure of quantum field theory and gauge theory in particular. So just to set some sort of notation, I want to just very briefly talk about some of the structure of tree-level gluon amplitudes. And of course, most people have probably seen this, but there's this sort of standard decomposition. So if I take my amplitude, I have got my various different particles. They're characterized by their momenta, which are on shell, the helicity of the gluon, and then whatever color, right? So these are colored particles. And so I can take my amplitude and I can decompose it. I can basically strip apart the kinematic part and the color structure. So basically, rewriting the amplitude as some sum over traces. So this A here has also the kinematic information, basically from momenta, and then this has the color structure. And this separation is often very useful. And so sometimes I'll talk about these color ordered amplitudes, and then sometimes I'll talk about the full amplitude, depending on which is more useful in a given moment. And then another, of course, key property is because the gluons are massless particles, these amplitudes are singular. There's infrared singularities. These, of course, are not really, in some sense, physical. If you calculate a physical quantity, the infrared singularities will sort of cancel. But they certainly show up at any intermediate stages. Actually, being able to deal with them as a practical matter is very important. But we also sort of recently have seen that these singularities in the amplitudes have sort of a connection with the underlying symmetries of the theory, and in particular have sometimes pointed to sort of additional symmetries that maybe weren't already obvious. In particular, what we talk about is asymptotic symmetries, symmetries acting on the boundary of space-time. I'll talk about that in a little bit. In gauge theory, there are sort of two different types of infrared singularities. There's one where the momenta of an external particle sort of vanishes. These are sort of soft, these are called soft singularities. And then there's another case where essentially because you can't tell the difference between two massless particles on top of each other and just one massless particle. So when two particles become collinear, there's generically a singularity in the amplitude, and these are called collinear singularities. I'm essentially entirely going to be talking about the soft singularities. These, of course, are important and interesting. It's just that we'll discuss them for the most part. Okay, so to try and talk a little bit about the structure of amplitudes as we sort of consider what happens as a momentum, as the momentum of an external particle becomes soft, we start with the sort of simplest case, the U1 gauge theories, just like Maxwell theory. And so, as I say, these singularities occur when one of the four momenta vanishes. So here I have sort of a schematic picture of some amplitude. S is some external leg that's going to sort of go to 0, and then the other legs are labeled. Well, I should have called it P, but I've actually called it K in the picture for some reason. And so what happens is that as one of, so this is a tree level. well, here that's enough. But yeah, so as one of the momenta becomes soft, the amplitude in some sense factorizes. So essentially there's a singularity where in the amplitude where this momentum k is on a shell, so it squares to 0, and so this gives rise to sort of a propagator in my amplitude, or in the diagram corresponding to my amplitude, sort of blowing up, and so this gives some singular factor, and the amplitude sort of splits into two parts, into some universal factor which I've drawn here as this red dot, and then an amplitude which has one less leg. Right? So this is some n-point amplitude. Here this is going to be some n-1 leg amplitude. So for photons and gravitons, this is sort of well-known result, but it goes back to Weinberg, even earlier for photons, where you get this factorization behavior. So if I look at this n+1 leg amplitude, Q is the momentum that's going to be going soft, and as in this soft limit, the amplitude splits into two parts, as I said, with some n-point amplitude, and then there's this soft factor, this red dot is given here, and the structure of this is somewhat interesting. It has this sort of so-called universal behavior in that it doesn't really care about what the other legs in the amplitude are. So here, this is some photon, but these could be anything. Yeah. So it depends on the momenta of the other legs, but it doesn't depend on sort of what type of particle it is, or whatever. But quantum numbers might describe that particle other than its momenta. Yeah. So this is it's universal in this particular. Okay. Sorry, it does depend on the charge and the form of momentum of the hard legs. Okay, good. So yes, that's gauge. That's a U1 gauge theory. When we go to Yang-Mills theory, it's a little bit more complicated. Basically, just including the color structure. So, but again, if I look at my n+1 leg amplitude, and so here in particular, I am looking at this sort of partial amplitude, this color-ordered amplitude. So I pulled off the color structure, and I let a leg go soft. And so one of the key things, which I probably didn't stress, is that in these color-ordered amplitudes, oops, yeah. So here, of course, this is the amplitudes are perfectly symmetric in all of the different bosons. But here, each individual term has a particular ordering. Right? That's why it's called color-ordered amplitude, which is sort of the ordering in the kinematics corresponds to the ordering in the trace. So that then, when I look at this amplitude, there's neighboring legs. There's sort of well-defined neighboring legs. So here I'm considering the legs 1 and n being next to my soft particle. And so in this soft limit, I still get this factorization behavior, but now the soft factor sort of knows where it is in the trace. So it knows about the two momentum on either side of it. So again, I can look at the soft limit. I get this factorization behavior, well, I'll write down the formulas in a second, but you do see this universal behavior at leading order. But what you can actually do is you can even ask, well, what happens if I'm making some sort of expansion in a small parameter in this momentum, the soft momentum S. So basically, if I introduce a parameter delta, which tells me how my momentum is becoming soft, I can expand the amplitude in this parameter, and I can ask, okay, so at leading order, I'm going to find this universal behavior, but what happens at subleading orders? And indeed, actually, it turns out that at subleading order, there is also sort of a factorization behavior, which is universal in a certain sense. In order to write down these soft factors, and often for much of this amplitude business, it's useful to use the spinor helicity formalism, which people have probably seen, but let me just very quickly describe it. So, all of my particles are being described by massless momenta, and so for a massless four momentum, I can sort of decompose it into a product of spinor variables, which are called lambda and lambda tilde. And this decomposition gives me sort of two different ways, or a number of different ways. So I can always scale the lambdas in whatever way I want, as long as I get the same scaling in the p. So it gives me sort of different ways of taking the soft limit. So for example, I could scale just lambda, or I could scale just lambda tilde. And I'll look at basically the case where I scale both of them the same way. So with this particular scaling, I'm using these variables lambda and lambda tilde, and also using these spinor brackets. So for example, if I take, I have some on-shell momentum, I decompose it into two spinors, I can contract the two spinor indices, which I have mislabeled. So here I should have called this alpha and beta. So here I called it alpha and then beta, or this should be alpha and alpha dot. So I can take the spinors and I can contract them using an epsilon tensor, and I get these angle brackets, or if I take the lambda tildes, I can get these square brackets. So these are sort of these angle square bracket factors that you often see in this on-shell, this spinor helicity formalism for writing down amplitudes, which is sort of just, it's just usually very efficient. So in particular, in using this notation, I can write down sort of the leading term. So as I was saying, if I decompose my amplitude, I get some sort of leading factor, and that is just given here. And as I said, you can sort of see it. So for a positive helicity, gluon becoming soft, I only get angle brackets. So it sort of only depends on sort of the holomorphic part of the momentum. Basically, it doesn't depend on lambda tilde. And it depends on it depends on the momentum of both of the neighboring particles, which here I've also assumed to be massless, so that I can also use the spinor helicity formalism for those particles. And then at subleading order, so as I said, I can go to subleading order and I find another factor. It has this slightly more complicated structure. In particular, it sort of involves derivatives. So this is now some operator acting on the amplitude. So as I take this limit, I get some soft factor, which is basically an operator acting on the n-leg amplitude, and it acts by sort of taking derivatives with respect to the adjacent momentum. But it's universal in a sense. So here I have assumed that the particles are massless, but it doesn't care, for example, about the helicity of the neighboring particles. So and also the subleading factor, and you could sort of imagine that as I go to this, I can always do this expansion, right? So if I take an amplitude and I expand in some parameter, I can always sort of, pull out the n-leg amplitude. But in general, this subleading term could start to depend on all of the hard momentum. And it doesn't. It still only depends sort of on the neighboring momenta of the soft particle. So it's still local in a certain sense, as in it only depends on the particles adjacent to it in the color ordering. And it's also universal in that it doesn't care about the helicity of the other hard particles. Okay. So you do still find this sort of universal local behavior in the subleading order. But of course, if you go to arbitrary orders, that's not going to be true. Okay, so this is the soft sort of expansion of the old gluon amplitude. This is tree level. Both of these are just tree level expressions. Yeah, okay. So the next thing that you might want to do is you might want to ask, okay, so what happens when we allow not just one particle to become soft, but we allow multiple particles to become soft?
There's a constant factor in the unity in the two brackets.
There's a
Constant factor in the unity of the brackets.
You mean like an overall scaling? Yeah, that's right. So that's right. So the scaling of the amplitude will have some fixed scaling depending on the helicity of the particles under and actually so this is in some sense information about the overall helicity of the particles in the amplitude. So it's not. So the actual thing is that there will be particular ratios of these brackets such that the scaling is fixed. The soft factor is not homogeneous. No, that's right. There's some definite scaling depending on the helicities of the particles. Okay. Yeah. Okay. So we can talk about the multi-soft limit. So here, basically, just sort of doing the same thing, but now allowing more than one particle to become soft. So here, I'm going to look at two particles becoming soft. So S1 and S2. And again, I could imagine taking these soft limits in various different ways. And again, I'll choose the same scaling for the lambda and the lambda tildes of the soft particles. But now I have delta 1 and delta 2, and you could imagine doing different ways. So for example, I could imagine first taking delta 1 to 0 and then delta 2 to 0. This is called consecutive limit. Or you could try and imagine doing some sort of simultaneous limit where you take both of them to 0. Of course, you can imagine other, this is just two sort of limits of sort of some parameter space of limits. Okay. The consecutive limit is in some sense trivial in that it's just, I just take the single soft limit and just repeat it. So for example, I can take the consecutive soft limit, just as I say, by taking two single soft limits, and so I just get basically products of these factors. And so just using the formulas from before, I can essentially just work out what I get again, and you can write these things down. So that's relatively straightforward. I'm not going to, I won't go through the formula right now. But there are a couple of things that are sort of worth mentioning. Is that again that there's sort of this universal behavior that extends. Sorry, let me say this again. Okay, so there's a universal behavior in the multi-soft limit. In this case, this sort of just follows, for the consecutive limit, this just follows from the universal behavior of the single soft limits. But there's an additional sort of simplicity in the case where the two particles have the same helicity, in that it actually doesn't care about how I take the limit. So in this sense, the consecutive soft limit is sort of, all limits, all different ways of taking the limits. However, this is not true at subleading order. So in that case, then you do have to be a little bit more careful. In the case where I have two different helicities, so if this is the case where I have, say, two positive gluons both becoming soft at the same time, if I have a positive helicity gluon and a negative helicity gluon becoming soft, then it does depend on how I take, whether I take a simultaneous or I take a consecutive, or some even more general combination. And so I find terms that depend on, say, the order of which. So I take the first one or I take the second one. And so here I have to introduce parameters that tell me, exactly what order I took my limits. If I want to take the limits simultaneously soft, so take both of them at the same time, then you can't use this sort of consecutive soft limit. So I have to sort of go back and look at the formulas a bit more general. And you can derive simultaneous soft limits using some of the standard techniques for analyzing tree-level amplitudes. So the way we did it was using BCFW relations, which we sort of heard about a little bit yesterday. I'm not going to describe too much about the technology of it, but in some ways it actually relies on also this factorization properties of amplitudes, right? So you take the amplitude, you consider it as a function of some complex parameter, and then you look at where the singularities are, and then you can sort of reconstruct the amplitude from lower point amplitude by looking at the residues of all the singularities in the amplitude. Okay, so by using sort of the BCF formalism, you can ask, you can analyze the soft behavior of the amplitudes, and you find sort of reasonably nice expressions for these double soft limits. In particular, though, what happens is that now, you find this sort of behavior here. So here I have Q12, which is the sum of the two soft momenta. So sort of the double soft limit, the factorized, the piece that comes in front of the amplitude now sort of depends equally on the two. Okay, so those formulas, I haven't gone through them too much, but essentially I just want to say they're sort of, you can, by looking at the amplitudes and looking at the techniques that we have for studying them, you can just sort of pull them out. And that's fine. So what we might want to ask then is, okay, well, what are they actually telling us about the structure of the theory? And so one thing to do is to rewrite them in a different set of variables. So I want to rewrite those expressions in a new set of variables. So I take my spinor helicity, my spinor variables. So here's lambda and lambda tilde. And I pick a particular parameterization. So I choose omega, which basically tells me sort of the overall energy of the momentum. And I pick a complex parameter C, which is essentially going to tell me the direction on the sort of sometimes called the celestial sphere. So basically what direction the momentum is pointing in. So in terms of these variables, the four momenta can be written like this. And here we can sort of see essentially that this is just sort of the, as I say, so omega is the overall scale of the momenta, and then the z and the z bar are the stereographic projection of the celestial, of the sphere. So basically it tells me what direction the spatial component of the momentum is pointing. So choosing these variables, I can then take these soft factors that I sort of previously wrote down. So here, this is this leading order soft factor for the gluon. I'm writing it in terms of the z, and I choose similar variables. So z is going to be tell me the direction of the soft gluon, and u is going to tell me the direction of all the other hard particles, which they're hard, but I do assume they're massless, as I said, so I can still parameterize them by some complex parameter. And so if you look at the soft factor, you can see that it essentially has poles as the direction of one of the soft particles approaches the direction of one of the hard particles. So this is, in some sense, this collinear limit. So in the collinear limit of the soft limit, the soft factor itself becomes singular. Okay, so I take these soft factors. So this is the factorization property of these color-ordered amplitudes that I mentioned. And now I'm going to sort of repackage everything back together again. So now I'm looking at the soft limit of the sort of the full amplitude. So I've put back in my traces and I sum over all the different permutations. And so I'm going to look at sort of, so this is the soft limit of the Yang-Mills amplitude, and I'm just going to sort of, as I say, sort of rewrite it a little bit. And I'm going to define, so this is really just a formal expression. I'm going to call J is some current acting on the amplitude, and this is just defined by taking the soft limit of my amplitude. And I multiply by some overall scale. So this is sort of the definition of what I mean by some current. So sticking in these formulas, rewriting it a little bit, I see that this object here looks like this. Here I have so T are the generators of the color algebra, the SUN. I take my color algebra, I take my color to my gauge group to be SUN. And so this is the color generator acting on the Lth leg of the amplitude, and it's acting just by the adjoint, right? So it basically just reaches into the trace and sort of acts by the commutator. And then there's some pole, right? So there's this pole. And so here I end up with some operator, so basically my soft operator, acting on my amplitude, gives me sort of this, gives me exactly this formula. And this sort of looks somewhat familiar, right? So as pointed out by Strominger and Strominger and collaborators, this expression here, this is just what I had on the previous slide, can be compared to the word identity for a two-dimensional Kac-Moody currents, right? So if I was doing two-dimensional current algebra, I would have, so I have some current generator, I'm looking at some correlation function of some primary fields in some particular representation, and then if I look at the correlation function with an insertion of this current, the correlation function satisfies essentially this same word identity, or satisfies an equation, a word identity, which looks exactly like this one, right? So I have this pole as the current approaches the location of any of the other fields. The residue is given by the color generator in the representation of the primary fields. So I can also just rewrite this in sort of this OPE language, and so the OPE of the current operator with the primary field is just given by this formula here, essentially the same factor that appears in the word identity. So in this sense, there is a formal similarity between the soft limit of the amplitude and the word identity for a two-dimensional Kac-Moody. In order to, so the idea is then, well, how far can we push this analogy? Is there really something going on, or is it just really simply just a formal coincidence? So one of the things that you could do is you can ask, right, so is there, what is the actual algebra? So if there are these currents, what is the algebra of these currents? Do they satisfy the same algebra that we would expect for current algebra? One way of asking what is the analogous quantity in the amplitude, so if we were looking at a current algebra, what we would want to do is we want to look at the current OPE. Right? So we would take two currents, depending on two positions on the complex plane, we let them sort of become coincident, and we would find this OPE structure. Right? So we would find some Z1 minus Z2 squared, and the coefficient of this is the level of the current algebra, and then the residue of the pole has the structure constants of the algebra times another current. If I took this OPE, and again, if I was doing two-dimensional field theory, and I took this OPE and I inserted it into some word identity, inserted it into some correlation function, I would expect the correlation functions then to satisfy this particular structure. So this is taking this OPE and plugging it in. So can I find this sort of structure in the amplitudes? And as I said, inserting each current corresponds to taking the soft limit of a gluon. So here, if I want to take two, I want to have two current insertions, I look at the double soft limit of an amplitude. So I take here the double soft limit of my gluon amplitude. And then I have to look at the behavior of the two currents as they become coincident. That's the collinear limit of, so this is the collinear limit of the double soft amplitude. So I take this limit, and indeed what I find is that I get exactly this structure here. So the amplitude in the double soft limit has this structure. So comparing this line here with this one, we can see that we get this second term. So we have the structure constants of the color algebra, but we don't have this first term. So essentially this is then interpreted as saying the level of this algebra is 0. So in that sense, it's not really Katz-Moody, it's just a simple current algebra, there's no central extension. Okay, so this then tells us, again, we at least can reproduce some part of this current OPE. And again, sort of pushing it forward, if we did have a current algebra, one of the standard things that you can do if you just open up a book on conformal field theory is you can do the Sugawara construction. I can take my currents and I can construct a stress energy tensor to construct a conformal field theory. So in that case, what I do is I take my two currents, I contract their group indices, and I take the singular limit. In general, if there was a non-trivial level, you have to sort of subtract off the singular part. Here, that's not the case, so it's even simpler. There's some particular normalization. This is just, in our case, this is just n. And so I can, so given two-dimensional current algebra, you can construct a holomorphic stress-energy tensor and hence a conformal field theory. Now, in what sense is this, in conformal field theory, you can then sort of show that given this stress-energy tensor, it satisfies the OPE with the current, it satisfies this OPE with the current. Right? So this is sort of characteristic of the conformal field theory. And so the question then is that, well, can we construct this holomorphic stress-energy tensor for Yang-Mills theory? Can we find a conformal field theory structure in the soft behavior of the Yang-Mills theory? So the analog of this holomorphic stress-energy tensor, again, each current corresponds to a soft limit of a gluon. So again, I'm going to look at some double soft limit of my amplitude. I'm going to take the collinear limit, and then I'm going to want to ask, does this operator, does it satisfy the appropriate OPEs? Does it satisfy the OPE I would expect from the Sugawara construction? So now, if I have my holomorphic stress-energy tensor, I want to calculate the OPE with the current. So I have two soft gluons in the currents that make up the stress-energy tensor, and then I want another soft limit from my third J. So now I need to look at the triple soft limit. I didn't write down the formula for the triple soft limit, but you can sort of just work a bit harder and you can find what that is. So I now look at the triple soft limit of my amplitude. This corresponds to 3 current insertions, and then I take this particular limit, and And if you do this, you do indeed find exactly this particular structure.
So what is curly J information?
So the curly J, so here is just something that I have. It literally is defined by the soft limit. I don't have. Okay, I'll come back to it a little bit. I don't have a independent definition of what curly J is. I'll try and, but it's meant to be something that lives. So it's meant to be a current that lives on the boundary of space-time. So there's some three-dimensional. Let me come back to this a little bit in a second. But at the moment, all it really is I'm pointing out that in the soft expansion of these amplitudes, it appears to suggest that there is something that is a curly J. The answer to your question is probably much more interesting than anything I'm going to be able to say, because that would be, well, what actually is it? But it seems to suggest that there should be something. But I can say a little bit more. Okay, sorry, I'm also running way over time. Okay, good. Yeah. So okay, so I can given that I have it looks like I can find some analog of this current. As I say, it's basically the soft factor of the tree level amplitude. And more than this, I can sort of take the collinear limit of a double soft limit to find what looks like an insertion of a stress energy tensor. And to really know whether I have a CFT, you would want to ask, well, what is the actual OPE of the stress energy tensor with itself? Right? So that would be the, do I really find the conformal algebra? So that, in that case, what I would want to do is I would want to find the OPE of two of these stress energy tensors. So now that means I have to have four soft particles, one for each J. So as I say, if this holomorphic stress energy tensor defines a conformal field theory, it would actually imply a ward identity for the primary field. So again, I would take one of these stress energy tensors, or two of them, I insert them into correlation functions, I look at the OPE, and this would tell me that the correlation functions have to satisfy this equation. And so I can ask, can I reproduce this ward identity for the amplitudes? So in this sense, I'm not actually constructing the J's. What I'm doing is I'm showing that the amplitudes satisfy the ward identities that correspond to some symmetries. And then you can ask what actually are those symmetries. And so indeed, you can do the same thing. You can look at the collinear limit of a quadruple soft limit for 4 positive helicity gluons, and you can see that the amplitudes do indeed satisfy this same ward identity. Okay. There is perhaps a reason for thinking that, so this seems to suggest that there is some conformal field theory that describes the soft behavior of gluon amplitude. There's actually, though, even it was pointed out by Kapak and collaborators that if you look at the soft behavior of a graviton, you can identify the soft behavior of a graviton with a ward identity for a 2-dimensional energy momentum tensor, for a stress energy tensor. So, and here we seem to have found a stress energy tensor in the behavior of 2 gluons. And this actually seems somewhat similar to work of, well, actually it's not maybe not so recent anymore, it's going back a few years, 4 years, of Stieber and Taylor, where they noted that if I look at the collinear limit of 2 gluons, those amplitudes look like the soft limit of a graviton. So that there is, in this sense, some, and of course, this has been seen in various different contexts, that 2 gluons sort of, in some sense, look like a graviton. And so here we perhaps see some similar behavior, if not exactly this behavior, or exactly what the connection is. Okay, you can actually go. One thing is you can actually go a little bit. You can go a little bit further. So as I was saying, in these soft limits, there's a leading soft behavior, and then there's a subleading soft behavior. And the subleading soft behavior also shows this universal behavior. And so you could ask, well, can I identify some current, some symmetry with this subleading behavior? Well, moreover, can I reproduce like ward identities corresponding to some current from this subleading soft behavior? And you can actually, you can do this, you can repeat the analysis, you can take the subleading soft, you can say this defines for me some subleading current, and you find that the amplitude satisfies this behavior. And you can ask, is this the Ward identity for some two-dimensional, some two-dimensional theory? So is this the OPE? So here I've rewritten this behavior of the amplitude in sort of in the notation of an OPE. So again, I would have some subleading current, I have some primary field, and the OPE of the field with the current is given by this behavior here. This is obviously a little bit more complicated. In particular, you can see I get this sort of derivative behavior, and also it depends. What's also important is it depends on the energy. So one thing that we saw in the leading behavior is that the OPE coefficients, they didn't care about the energy of the hard particles, whereas this does. So now I need, there's sort of an additional quantum number describing the additional insertions in my amplitude that depend, and they know about what the energy is. So this sort of actually suggests that there's some sort of non-compact current algebra to describe these subleading behaviors. You can actually, again, using the multi-soft limits, construct what the algebra of these subleading soft currents are. And so you can find what the OP of the subleading currents with the leading currents, and they actually transform into the adjoint representation. And then you can find the OPE of the two subleading currents with each other. And at this point, you do start to notice that the ambiguity sort of of how you take the soft limits appears. So there sort of seems to be families of algebras which depend a little bit on the definition of your soft limits. Okay. So this particular structure, I don't know of a sort of a well-known theory, conformal field theory or whatnot, that actually has this structure, although it is somewhat similar to some non-compact algebras. Okay, so also to try and answer your question a little bit, it's not so surprising that we do find this current algebra behavior in the soft limits of the amplitudes. Because it is known that the soft limit is related to the Ward identity for the asymptotic generalized color charge. So at least in part, the answer to your question is that the currents correspond to these charges. So let me just say a little bit about what they are. So F here is just the normal Yang-Mills field strength. So essentially, this is just the standard usual definition of the electric charge. So this is the Yang-Mills generalization of the electric charge. In this case, I wanted to find the integral over some surface, right? So I have my usual Gauss law, right? So I integrate over some volume, and then the charge inside that region is related to the electric flux passing through the surface. So here I have the same thing, but I need to tell you exactly what surface I'm going to integrate over. And in this case, I'm going to look at amplitudes defined in normal flat space. And so I need to talk about what the boundaries. We also saw sort of like this picture here. So this is the Penrose diagram for flat space. Perhaps this is a little bit too small, but the asymptotic region so if I take R going off to infinity, while so if you look at outgoing light rays, these will sort of go out to the sort of null boundary of space-time, which I've called scribe plus. This is parameterized by some parameter u. So here, if I take so I take my normal metric, and I use the sort of normal spherical coordinates. U is just t minus r. So I'm looking at the sort of the large so the large R region here, and U is the parameter along the null boundary. And so on this, so this boundary of space-time is three-dimensional. It's parameterized by a null coordinate U and a two-sphere. So at each point along the boundary, there's a two-sphere. And in order to define the charge, I integrate this quantity to basically the field strength. Of course, this is not abelian, so I'm taking the trace. I have some parameter epsilon, which characterizes the various different charges, and I integrate over the scribe plus. I have a similar charge that I can define on past null infinity, and then these are actually related to each other in a particular way that actually won't be necessary for what I want to talk about. If I take this charge, I can sort of use the standard expression for what the field strength are, and you'll find that there's sort of a linear piece, basically linear in the gauge potential, and a non-linear piece, right? So that would be sort of the non-linear part of the field strength. And would also involve whatever other charges. So if I have quarks or if I have anything else, it will depend on the charge of those particles. If I take my theory and I just linearize around flat space, so basically I take my potential and I just use, I use the normal oscillator expressions for my field strengths. I can actually write down the linear charge in terms of the oscillators that basically correspond to small fluctuations, small gluon fluctuations around the trivial background. And so the linear piece, written in terms of the oscillators, essentially looks like this. And so what does it actually involve? So here, of course, this is sort of the annihilation operator for a negative helicity gluon. This is the creation operator for a positive helicity gluon. The gluon has some energy, which basically corresponds to omega, like I mentioned before. Z, as I say, tells me what direction the gluon is going in. X hat is the unit vector, basically corresponding to Z. And the linear charge is corresponds to the soft limit. So I take the energy soft of the particular gluon. So you essentially just take the expression that I wrote down here to say it's essentially just the standard expression for the charge. Sub in the normal mode expansion for your gauge potential, and you find that the linear charge is related to a soft gluon. And then, as I say, there's actually a nonlinear piece which would involve it essentially involves the charge density, the color charge density of whatever other quarks or gluons that I would have. It's a little actually bit ambiguous, and it's often sort of actually just left out of the normal definition. We'll actually see sort of how it kind of arises from our construction. Okay. Now, so we sort of want to connect these these charges. We want to know, how do these charges act on the scattering amplitudes, and how are they related to the soft limit? As we can sort of see, they are naturally going to be related to the soft limit. They correspond to sort of sticking in a soft gluon. But we want to know, what is the action of these charges on the scattering amplitude? Essentially, what are the Ward identities? These sort of the same expressions that I had before. How can we derive those expressions from these charges? There's a bit of a problem in trying to do this, in that the scattering amplitude is not actually well defined. So this was sort of something that, at tree level, the scattering amplitude for generic external momentum is fine, but when you try to go beyond tree level, you find that the S matrix is in some sense not strictly defined because of these IR divergences. In some ways, if you take the IR divergences and you calculate them, the amplitude vanishes. So of course, these things are not necessarily physical, but it's, we want to talk about the amplitude, we want to talk about the symmetries of the amplitude, so we need a slightly better way of sort of formulating things. And one way of doing this, which goes back to work Dollard in quantum mechanics, and looking at the Coulomb interaction, and by Faddeev and Kulish in QED, is this method of sort of coherent states. And this was sort of generalized to Yang-Mills by Catani and Ciappelloni back in the 80s. It's really quite an old method. And the idea is to sort of look at something that is the so-called finite S matrix. So it's an analog of the S matrix, but instead of using the normal Fock states, you use these coherent states. And very quickly, the idea is that I take my interaction picture Hamiltonian, and I split it into two different parts. So I look at, in any interaction, I pick some energy scale, and I look at, so there'll be sort of gluons, bouncing off each other and exchanging energies. And I take my interactions and I split them into those interactions which involve transverse energies below some scale and transverse energies above some scale. And I say that the part above is the hard part of the Hamiltonian, and the part below is the soft part of the Hamiltonian. And I take these two parts, and then I'm going to take my soft Hamiltonian, and I'm going to use that to define my sort of asymptotic states, and I'm going to take the hard Hamiltonian and use that to define my S matrix. So in particular, so I won't give too many of the details, but I take my hard Hamiltonian and I use this to define these standard Muller operators, right? So I take the time-ordered exponential of my soft Hamiltonian, so it's the usual thing you can do. Now, if I take this, so in QED, this all just works fine. In Young-Mills, it's a little bit more complicated, again, because of the self-interactions of the gluons. And so I can't actually get everything. So I have to make a slightly further approximation. This is what I'm going to make in this talk, although you can do a bit better. And that you look at only the leading IOR divergences. So at every order in loop expansion, you'll find, as I say, that the amplitude is divergent. If you pick some regularization, you'll have some expansion in that parameter. And so we will just, for the moment, just look at the leading IOR divergent part. So we'll look at the finite S matrix, but it won't be entirely finite. It'll just be missing the leading IOR divergence. In that case, so actually, what time do I finish now?
I have about 5 minutes.
I have about 5 minutes. Okay. Yeah, I'll have to go a little bit quicker. All right. Okay. If I look at just the leading IOR divergence, I find that these Muller operators have a particularly nice structure. So here it's written as a time-ordered exponential, but I can sort of go to energy momentum space, and then I can make some approximations, as I say, which corresponds to focusing just on the leading IOR divergence. And I find that I get this energy-ordered exponential, and it involves sort of 2 terms. It involves this pi, which essentially is the displacement operator, and it's the fact that this combination of the oscillators appear. This looks like the normal coherent state that you find like in the harmonic oscillator in quantum mechanics, where you find this particular combination when you look at coherent states. And then there's this factor J, which here depends on rho. Rho is the, as I say, the color charge density of my theory, so it involves whatever the colors of the gluons, whatever quarks, and it has this particular kinematic factor as well. This, of course, I've called this J because this also is the same soft factor that you see that we saw at tree level. So sort of we find this behavior of this sort of displacement operator times this soft factor in these Muller operators. And so we take these soft Muller operators and we use these to pull off the IR divergences from the S matrix. So essentially I'm going to define an IR finite S matrix. So I take my standard S matrix, the usual one defined in perturbation theory, and I contract it with these coherent state operators. And these, as I say, sort of remove the IR divergence. And this is this picture here. We think of these operators as sort of adding sort of clouds of gluons, of soft gluons. So here, in this operator, I'm only integrating up to some scale E. So these gluons here are all soft, right? They all have energies below whatever soft scale or whatever scale I've picked E. So these are all, this is some then, onto each leg I add this cloud of gluons, and this cloud of gluons essentially, accounts for all of the interactions of my final initial states and removes the IR divergences that are due to those interactions. So here actually I can define new states, I can define a new S matrix, or correspondingly I can define new states, which I use this sort of double bar notation, which is defined using these Muller operators. And then correspondingly, so I'm probably running out of lots of time. So there's a very nice feature though, is that actually this Muller operator, of course, depends on the entire S matrix, but at leading order, you get sort of a cloud of gluons associated with each external leg, so in some sense factorizes. So I get sort of one operator for each external leg. Okay. So yeah, using these new states, we can then sort of go ahead and try and calculate what the various action of our charges on our S matrix are. So if we take these operators, and if we take our linear charge, we could, so the S matrix is defined in the far past and the far infinity, where the theory is linearized. And so in this case, we would expect that it's the linear charge that should act on our asymptotic states. But now we see we've introduced this sort of evolution operator, this Muller operator, and if we take the commutator, the action of our linear charge with our evolution operator, the evolution operator is meant to take you and sort of evolve you to finite time, where the theory is now sort of non-linear and sort of interacting. And so this evolution operator should tell us what the non-linear charge is, or also what this hard charge is. This is this other piece that I dropped off. So if this was true, then we would find that the matrix elements of the commutator of the linear charge with the S matrix should be given by matrix elements of the hard charge with a finite S matrix. And so this relation here is what I would call my Ward identity. So if I knew my charge, this relation here would give me a condition on my S matrix elements. And essentially, this is the same definition that sort of other people have used. Now, if we actually go ahead and calculate the commutator of the linear charge with the evolution operator, we find that in fact there's actually an anomaly, that we don't just get the hard charge that we would expect. But this anomaly only involves soft gluons, and so we can actually hope that it vanishes when we actually evaluate matrix elements of this commutator between dress states. Okay, and so this indeed is actually what happens. So if we compute matrix elements of the linear charge with the S matrix between dress states, basically corresponds to evaluating these two diagrams, we find the following relations. We find that the commutator of the linear charge with the S matrix essentially gives us action of the hard charge on the tree level amplitude. So this equation here, this is essentially the soft factors that I had before. And so we find this particular, so this is the same formula that I had before, but here I can now actually tell you what this charge is. It's what I wrote down previously, and this is what I found on the right-hand side. These are these soft factors that I'm now calling the nonlinear part of the hard charge. And indeed, I'm calling them this, but they actually also have exactly the sort of the structure that I would expect. They depend on sort of they count all, they're part of the charge density. So they count all of the different color particles that appear in my amplitude, and then give them the appropriate soft factor. You can then move to higher orders. You can, using this finite S matrix, you now find that I can calculate the commutator of Q with S, and you can ask, what is the one-loop correction to the Ward identity? There's a little bit of an ambiguity in this calculation, but by choosing a particular ordering of the soft factors, you actually find that the Ward identity is uncorrected at one loop. So in this sense, the Ward identity that you found at tree level that I wrote before doesn't receive any loop corrections. Okay, so just to finish, what are we actually seeing? So we see that at tree level, if you look at the soft behavior of the amplitudes, there seems to be this structure of some current algebra that then can be extended to the subleading order, where you find a slightly more complicated algebra that I don't know any before. You can try and interpret, so this gives you sort of a leading and a subleading behavior and gives you this algebra structure. You can then ask, so all of that was at tree level. The leading order can be identified with these asymptotic symmetries. So this gives some sort of interpretation, at least to the leading current. The subleading one we don't have. And then you can ask, well, can we extend this to the loop level? And you can extend the definition, you can extend the action of the loop level charges. Sorry, you can extend the action of the charges to loop level if you use this finite S matrix construction, at least to the leading IOR divergence. Of course, what you would like to do is, one, is there anything useful about this algebra? What can we actually do with it? Can we use it to derive some sort of differential equation? In conformal field theory, in the current algebra construction, you can use the current algebra construction to derive Collinear-Zamolodchikov equations, which are some differential equations for your correlation functions. And you can ask, well, could we do the same thing here? Can we extend our construction to subleading order? Can we, our loop considerations, can we prove the existence of these subleading charges in subleading order? And one thing that might be very useful would be to actually make contact with this SET formula. And then, of course, really, one key thing is that is there actually a more fundamental interpretation of these two-dimensional theory? Is there some theory on the boundary that could calculate these amplitudes without having to do a normal, field theory calculation? Is there some holographic, flat space holographic description of these amplitudes? Okay, with that, I'll thank you very much. Thank you.
Other questions?
So, hold on, sorry. Yeah, no, this here, this integral, so this charge does just come, so is just the charge that follows from Noether's theorem. So essentially, but by using, so here, this is an integral over three-dimensional space. So the boundary is this square plus is a two-dimensional sphere times u, and this is an integral over the three-dimensional boundary. But yeah, so when I write this formula here, I've actually I can perform the integral over u, and it's the integral over u that's essentially giving me this soft language.
And this comes from functional momentum.
So yeah, so in that case, I'm parameterizing the momentum by z, and I'm actually doing the same thing here. So yeah, so basically this z here tells me the direction of the momentum of the gluon.
So how does this relate to symmetric sphere, which is a spatial configuration?
So if I have a momentum, it points in a direction in space as well, right? So so if I have a momentum, it gives me, it's a vector in space. It picks a direction in space, and so there's this connection. There's this connection between, yeah, and it's a slightly unusual one, right? So I'm not doing, and you do find that in this case, yeah, in these soft limits, there's sort of a momentum space, the direction momentum space, and direction in space time get tied together by this soft limit. So yeah. It's probably a better answer for this, but it is literally that yeah, the momentum is a vector in space, and it's that direction. It's the direction on the screen.
Yeah, I have another pragmatic question. So is QCD finite in some sort of collision factor? Infinite finite? There was a big this is really controversial.
So you're saying, so can I remove all of the IO divergences? Okay, so here, this method that I'm talking about will remove the leading IO divergence at all orders, all loop orders. Ciappelloni and Catani have a prescription for doing the subleading order. I don't know for proof that you can remove all orders at all loop order. However, I think this SCAT method, which I guess, I think, so there's this paper by, as I say, Hannesdotter and Schwartz, actually, which is quite recent, and they attempt to use this SET formalism to define a finite S matrix, including, so one thing that I didn't make clear also is that the leading IR divergences don't include, I'm not including the collinear divergences. And so this formalism here, it's meant, the claim is that it will remove all the soft and collinear divergences, and that the S matrix defined this way is perfectly fine. I don't know if that's been proved at the moment.
Are there more questions? If not, let's thank the speaker.